Well, not so simple, but what we have now seen is light has particle nature. Now, let's look at the double slit experiment Thomas Young did. Now, what Thomas Young did is he cut two narrow slits on a screen and allowed a monochromatic light, a light of one color, to pass through the two slits. And what he observed on the screen is actually bright, dark fringes. Now, how is that possible? So Young sent light from monochromatic source through two narrow slits and showed that interference patterns can be seen on a screen placed behind it. The interference pattern was a set of alternating bright and dark lines. The bright fringe in the middle is caused by light from the two sources traveling to the screen the same distance. In other words, there's no phase difference. That's called the zero order fringe. The dark fringes on either side of the zero order are caused by light from one slit traveling half a wavelength more than the light from the other. That means light from one slit meeting with light from the other will be out of phase there and producing a dark fringe. This is followed by the first order fringe. You see this zero order, the first order, the second order. This is where light from both slits are in phase, they travel the same distance. The first order fringes are produced when light from these two arrive in phase again. A dark fringe when they are out of phase, and so on. Now, let me see if I can demonstrate that to you. I have here a source of light and a number of slits cut on a dark glass plate. And if you look at one of these, can you see this as a double slit? Well, it is a double slit. There are two white openings. Now, I'm going to let light pass through these, and I'm going to keep it in front of the camera and see whether you can see the different orders of the fringes. Alright? Now watch the interference effect when I keep the double slit in front here. Well, I think I need to make a little adjustment. Give me a second. Watch this. This is a very good interference pattern produced. You can see the zero order and the different other orders. Alright. Now that's a very good one too. I'm using different slits actually here. Alright. Here I have a diagram of the arrangement I just showed you. This is the source of light, the light bulb, and this is the double slit. The distance between the two slits is D. Let's do a little theoretical interpretation. For two slits separated by a distance D, the path difference. Now, I don't think you can see the point where on the screen the light from this slit and this slit meets. That means the path difference is actually this distance. That is the path difference. Now remember our discussion on wave motion. If the path difference is an integer multiple of a wavelength, then the waves will be meeting in phase. So if this path difference is 1 lambda, 2 lambda, 3 lambda and so on, these two lights will meet in phase producing bigger light. On the other hand, if this path difference is an odd integer multiple of half a wavelength, 3 halves of a wavelength, 5/2 of a wavelength, then the two waves will be meeting out of phase. That means there will be dark, light, and so on. So bright fringes correspond to d sine theta equal to m lambda, where m is an integer, 0, 1, 2, 3, and so on. M equal to 0 correspond to the central maximum. That's what's called the zero order. Now dark fringes correspond to d sine theta is m plus 1/2 times lambda. This is how we write an odd integer multiple of half a wavelength. M equal to 0, this will be half a wavelength. M equal to 1, it will be 3/2 lambda, and so on. And whenever the path difference is an odd multiple of half a wavelength, you have the resultant wave will be 0. So here m equal to 0 correspond to two dark fringes, one on each side of the central maximum. So here again is the picture. If theta is the angle that corresponds to the bright fringe, suppose this is the central maximum, and this is the bright fringe corresponding to order m, mth order. It can be 1, 2, or 3, and so on. So if theta is the angle corresponding to the bright fringe of order m, then y is the distance of that bright fringe from the center, L is the distance between the slit and the screen. Look at the geometry there. Then for small angles of theta, sine theta is the same as tan theta equal to y/L. Now this relation is true only when the angles are small. Now d sine theta equal to m lambda. D sine theta is that phase difference. Remember the path difference there? When that path difference d sine theta equal to m lambda, that corresponds to a bright fringe. That means lambda equal to d sine theta over m. So if you can identify a bright fringe which is at the mth order and measure that distance y, you can actually calculate the wavelength. So lambda equal to d sine theta divided by m, where I'm going to replace sine theta by y/L. So lambda equal to dy divided by ml. So what does y stands for? Y is the distance of the mth bright fringe. That is, it can be the second, third, fourth, whatever you choose. From the center, L is the distance between the slits and the screen, and M is the order of the fringe. D is the distance between the two slits. You can calculate the wavelength of that light. In fact, that is a very effective way of doing. I'm sure if you go and major in physics, you will be doing this experiment as a junior in the college. Let's do a small problem. Two coherent microwave sources that produce waves of wavelength 1.5 centimeter are in the XY plane. One is at 0.15 centimeter and the other is at 3 centimeter, 14 centimeter. If the sources at these points are in phase, find the phase difference of the waves from these sources at the origin. Well, the distance of the source at 0.15 from the origin is d1 equal to 15 centimeter, because this is placed at x equal to 0, y equal to 15. That means the distance of that from the origin is 15 centimeter. It needs no explanation. the distance of the source placed at x equal to 3, y equal to 14, what is the distance of that source from the origin? It will be square root of 3 squared plus 14 squared, that is 14.318 centimeter. So, one source is 15 centimeter from the origin, the other source is 14.318 from the origin. Now, what is the path difference between these two waves? The path difference will be 15 centimeter minus 14.318 centimeter, which is 0.682 centimeter. Well, since one wavelength is 1.5 centimeter, the path difference of 1.5 centimeter is the same as a phase difference of 2 pi radians. I hope you understand. We have discussed this in wave motion. A path difference of one wavelength is the same as a phase difference of 2 pi. A path difference of half a wavelength is the same as a phase difference of pi. And therefore, if a path difference of one wavelength is the same as a phase difference of 2 pi radians, that means in this case, a path difference of 1.5 centimeter is the same as a phase difference of 2 pi radians. What will be the phase difference corresponding to a path difference of 0.682 centimeter? I can leave it for you. You will be able to do that. A path difference of 0.682 centimeter corresponds to a phase difference of 0.682 divided by 1.5 multiplied by 2 pi, that is 4.3 radian or 164 degrees. That is the phase difference between the sources at the origin. That means if you use this value of delta in the equation for, what's the equation for the resultant amplitude? 2E0 cos delta by 2. If you now use the value of delta there, you will be able to obtain the resultant amplitude at the origin.